No. I know it's 295. 3 times 12. 36. You don't have competition. Well, even if I did keep it for the whole time, if I did a whole year of 36, then I'm only going to do 1 month more. Instead of having to rebuy another. Oh, yeah. Or just a 2. Next year, just the 1. I probably should have done that. I think we're the same. Another one that I was missing. You're right. So next semester, or next oh.
Yeah, how's it going?
That lecture is going to be online on.
Yeah, I made it back in time. Because I had a plumber come by to check my water heater today. He's like, I'll be there sometime between 10 and 2.
Oh, wow.
I was like, what the heck?
That's any
Yeah.
time.
Yeah, so I wasn't sure if he's gonna be there, but he came at like noon and he finished up at 1. So I just drove to campus
Oh,
after
yeah.
that.
That's fun.
Mhm.
Oh, there it is. What about the meeting stuff? Give some time. Oh, now it's just, yeah, there you go. Now. This is just it. Yeah. This is just it. Should be on.
Oh, maybe that's why there's two.
Yeah.
I don't know, you can edit it. It's just there.
Okay. I cannot believe this. Yeah. Oh, it is. There.
Now this.
Trent?
Yep.
How in general can we be in our understanding of one D equations for 422? Because I know they're derived from Navier-Stokes.
Yep.
momentum equations, but it's just saying that enough, I guess not, right?
I mean, you should know that, you should know kind of why we did the general steps, like why we took the integrals and things like that. And how we went, because Navier-Stokes you solve for velocity, and how did we get flow in the 1D equations? And so, kind of what that process was like. Yeah, not actually the mathematical details of that process, but just,
Why do we even do it?
exactly.
That's
Yeah.
interesting.
Mhm.
Hey, there's.
Okay.
That's what you want. I'll reach.
All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. So I know in the email last night I said we were going to do a virtual lecture today. That's because I had a plumber come in to check my water heater, and he said that he would show up anytime between 10 and 2. And so I wasn't sure if he's going to show up at the tail end of that time frame or the beginning. And so, I didn't want to just leave you guys in the lurch right here. And, and I didn't want to email you guys in the morning and saying that, we're going to be virtual. And so, that's kind of where the whole mix up came to be. But, he came at about noon, he finished up at about 1. And so I was able to come to campus. And so that's the reason why I'm here in the classroom with a few of you here in the classroom with everyone else on Zoom, right? So thank you. So sorry for kind of the mix up and the confusion, but we're gonna carry on with the lecture as normal. Okay. All right. So how's everyone doing today? Tired? I understand. Yeah, we just took a midterm, and so I know it's post midterm tiredness, and then we have finals coming up very soon too, and so it's definitely the stressful, tired time of the semester. Speaking of that midterm, I haven't started grading it yet, so my plan is to actually start grading tomorrow, so I should have those ready for you guys back by Monday. Okay, and maybe sooner depending on when I grade it. Okay, but Monday at the latest. Okay, so the plan for today is we're going to continue with our lecture notes on radiation. Okay, there is one more homework that I have planned for the semester, and so that's going to be due the Friday of the last week, and so 2 weeks from Friday, so about 16 days from now. I'll probably post it tomorrow morning, and you guys will have about 2 weeks to get that, and that's going to cover all the radiation stuff. Right? Okay, and so that's it for my announcements. And so are there any questions I can answer before we get started? Okay, all right, so let's go ahead and continue. All right, so last time we were here, we talked about this idea of radiation, right? And in fact, radiation actually shares a lot of similarities with, how we understand optics and light waves, right? Thought I fixed that. Well. Okay. Right. And so, a lot of what we understand about light, about, how it travels, how it, reflects off stuff, radiation behaves exactly the same way because, it's actually literally the exact same thing. It's just, radiation is just energy or heat traveling along those electromagnetic waves instead of just light. Okay. And in fact, last time we talked about this idea of intensity, right? And this idea of intensity was, this idea is that, even though we know that every single object emits radiation, the intensity is kind of a way to quantify how much heat is being given off a certain object, okay? Okay. And so similar to how you think about light, right? And so if you think about light bulbs, there are very dim light bulbs that you can hardly see, but then there are the really bright, intense ones, right? So it's like the difference between low beam and high beam headlights, right? And so we have that exact same concept for radiation. So we kind of introduced that idea last time, but today I wanted to kind of talk about that a bit more about how we can actually compute this. And so last time we talked about intensity kind of as a concept. Now we're actually going to quantify and see a formula for how we can actually compute that. Okay? And all this falls under the category of what's called black body radiation. Okay? Okay. And so let's recall the definition for a black body. And so a black body is an object with perfect emissivity and perfect absorptivity. Okay? Okay. And so their coefficients, the epsilon coefficient for emissivity and the absorptivity coefficient alpha, both of those are equal to 1.0. Okay. And so that means when it emits radiation, it does so with, you could consider it perfect efficiency. And then when it accepts radiation, or when radiation hits it, it absorbs it with perfect efficiency as well. Okay. And so, the idea of a black body is more of a theoretical kind of concept. And so, there are certain objects that get close to black body behavior, but none actually truly embody. Okay? And so it's almost like the idea of like a frictionless surface. Okay. Okay. And so what we say is that the idea of a black body is more of a theoretical idealization more than anything practical. But when you're first learning something, like when you're first learning mechanics, the frictionless surface really helped to kind of learn it for the first time. And so we're going to take that same approach here with radiation as well. Okay, so even though there's no such thing as a black body, in terms of learning from a learning perspective, it's good. Okay. And so the nice thing about a black body is that there's a formula that we can use to quantify its intensity. Okay. Okay. And so it's given by the following formula. So we have I for intensity. Okay. And so this is going to be a function of two main things primarily. So it's going to be a function of lambda, where lambda is the wavelength of the electromagnetic wave. Okay. And of course, it's going to be a function of temperature as well. Okay. So this lambda here is wavelength. Okay. And this T right here is temperature. Okay. And so it's given by the following. And so we have 2 times H times CO squared. Okay. And I'll define, and so those are constants. And so I'll define those in a second. Okay. Divided by lambda to the 5th power multiplied by e to the power of HC naught divided by lambda KBT minus 1. Okay. And so it's not and so I'll be the first to say it's not the cleanest equation. It's pretty messy. But then again, when you're talking about electromagnetic waves and optics, a lot of equations kind of tend to end up looking like this. Okay, so let me give the values of these constants, and so each of them have a name. And so first we have H. Okay, not to be confused with convection. This is optical H. Okay. And so this is known as Planck's constant. I know that's his name, but I always feel silly when I say Planck, because it looks like Planck, like from Ed, Edd and Eddy. All right, so the value of H is 6.626 times 10 to the minus 34. Okay, and the units for it is joules second. Okay. KB right here is another constant that's attributed to Boltzmann. Okay, so this is another Boltzmann constant. And so this has a value of 1.381 times 10 to the minus 23. And the units for this is joules per Kelvin. Okay. And C naught right here, this is the speed of light in a vacuum. Or in other words, this is the maximum speed of light that that light waves can occur. Okay, and so this value is 2.381 almost 3.0, but 2.998 times 10 to the 8th meters per second. Okay. And so that's the fastest thing, you know, known to man. Okay. And so there's that equation. And so, you know, this is not an equation that we'll use, you know, practically speaking. And so I'm not going to ask you to plug in for this, but what we are going to do is we're going to look at the behavior of this equation, you know, as lambda and as t vary. Okay. And so, you know, the details of this equation is not that important. You know, we're not going to plug into this, but we want to see how this varies as a function of lambda and t. Okay. Okay. All right. Any questions on this so far? Okay. All right. And so let's go ahead and see how that varies. Okay. And so let's look at temperature first. And so it's a little bit hard to see because temperature is pretty buried here and it only shows up once. Okay. And so the only place that temperature shows up is there. Okay. And so it might be a little bit hard to see because, you know, generally speaking, when you look at a formula, you want to ask yourself, you know, how does the formula change when T goes up or when T goes down, right? Okay. And so let's ask the question, you know, how does intensity vary with temperature? Right? And so you can see, you know, first of all, it's in the denominator. It's also in an exponential term, but it's in the denominator of the exponential form of the exponential term, which itself is in the denominator of this equation, right? And so it's kind of a tongue twister, but, you know, I'll just go ahead and say that as temperature goes up, intensity also goes up, okay? Okay. And that's consistent with what we already know, right? And so generally we know that as objects heat up, as they get more and more hot, then they should radiate a lot more energy, right? And so the surface of the sun, you know, we know is extremely hot. And so I think the sun has a surface temperature of about 5,800 Kelvin, right? And so because it's so hot, it's so intense that, you know, all the heat from the sun can travel all the way to Earth and make today extremely hot. Okay, and so that's pretty straightforward. And so now let's look at wavelength. Okay, and wavelength is a little bit more complicated because the dependence is not so straightforward. Okay, and so we have this. Okay, so we have obviously lambda to the 5th. Okay, and that's in the denominator. But we also have a lambda here in the exponential term, kind of in the same vein as t as well. Okay, and so the dependence on lambda is not so straightforward. Okay, and so what we say is that the intensity dependence on the lambda depends on the band. Okay, and so let me draw a graph for you. Okay. Actually, let me do just so the colors make a bit more sense. Okay, so let's do this. Okay, so on the x-axis here, I'm going to do wavelength. Okay, and so the units for wavelength are going to be in micrometers. Okay. Whereas on the y-axis, I'm going to put intensity. Okay. It's a little scuffed, but that says intensity. Okay. And so what you'll see is something like this. Okay. And so for a given temperature, and so let's say that we are considering we fix the temperature We fix it to be 1000 Kelvin as an example, okay? The intensity is going to vary like this. And so at first it's going to come up for low values of lambda, and then it's going to come down, okay? Right, let's do another one. And so let's do T is equal to 2000, okay? Right. So we're at a higher temperature here, and so the intensity should be higher, but the band is also going to shift, okay? And so it's going to shift more towards the lower values of lambda. Okay, so it's going to look something like this. And so I kind of, let me draw it a little bit better. And so, you know, the peak of the of this curve is going to appear at lower values of lambda. So let me go ahead and do this. Okay. That's a bit better. Okay. And then we'll do one extreme case. And so let's do the surface of the sun. And so the surface of the sun is 5800 Kelvin. Okay. And so it's going to be even sooner. So it's going to be somewhere like up here. Okay. But the decay is about the same. Okay. Okay, and so this kind of shows you the you know, the behavior of intensity versus wavelength. Okay? And so the upshot is that, you know, for a given temperature, you know, there are a band of wavelengths where the intensity is significant. Okay.
Professor, when you say band, are you referring to the curve?
Wait a second. Sorry.
When you say band, are you referring to the curve that we're being shown?
No, band means a region, and so what I mean is like this in between these two wavelengths right there, and so I call that a band of wavelengths. Yeah.
Gotcha. Thank you.
Mm-hmm. And what's interesting is that, you know, I drew the curve for the sun for a reason. Okay? And so if we draw a specific band, and so it's not, maybe it doesn't encompass the whole peak, you know, but it might look something like this. Okay. And so if I draw a peak, or if I draw a region like this, right? And so this region right here encompasses most of the peak for the sun. Okay. This region right here is the visible spectrum of electromagnetic waves. Okay, so these are the ways that we can actually visually see. Okay. And so the sun being at its temperature that it is, you know, it's you know, the amount of electromagnetic waves that hits the Earth that you know, that give us heat. That's also the same range that's visible to our eye. Okay? And so that's why, you know, as humans, we kind of have this association between, you know, what we see as light and what we feel as heat, because, you know, that's you know, that's kind of what we get from the sun. Okay. Any questions on this? Okay. All right. Let me write one more formula here. Okay. Because if you recall from last time, right? If you have the intensity of a particular radiation source, you can also compute its emissive power as well. Okay. Right. And so this formula right here is for the spectral, what we call the spectral emissive power. Okay. You know, whenever you see the word spectral in sciences, what that means is you're talking about spectrums of wavelengths. And so it has to do with wavelengths and it has to do with optics. Okay. Because I know spectral can sound like ghosts, but it has nothing, there's nothing spooky about this. It's about wavelengths, which is unfortunately a lot more boring, but you know, that's the word that science came up with. Okay. And so if you recall from last time, you know, the way that we can obtain spectral emissive power or emissive power, excuse me, from intensity is we just multiply by pi, okay? And remember the significance of that pi is the kind of the surface area of that hemisphere that can surround an object, right? And so we said that, for an object, it emits radiation in all directions equally. And so if we put a dome around an object, then that pi would kind of be like its normalized surface area, okay? And so we can apply this as well. And so we can take our formula for intensity up here and just multiply it by pi, okay? And so if we do that, the spectral emissive power, which is going to be a function of lambda and t, is going to be equal to 2 pi h c naught squared divided by lambda to the 5th times exponential h c naught divided by lambda kb t minus 1. Okay. So I just took the equation up there and just multiplied it by pi. That's basically all I did. Okay. Okay. All right, and so that's kind of how we quantify intensity as a function of wavelength. Okay? One thing that we might be curious about is that for a given radiation source and its given temperature, we might be interested in what wavelength does the peak intensity occur. Okay. Okay. And so for a given temperature, how can we compute that maximum wavelength? Okay. And so, one way we can do it is we can take this function right here and, do it just like we do in calculus. And so we take the derivative and we set the derivative equal to 0. But I don't know about you, but looking at that function makes me not want to take the derivative at all. And so, luckily someone else kind of felt the same. And so we came up with a much easier way to define this. Okay? And this is what's known as Wien's law. Okay. And this is much easier to determine. So what we say is that the lambda max, okay, multiplied by temperature, okay, because remember the maximum depends on the temperature. This is equal to 2,898. Okay. And the units is micrometers Kelvin. Okay. And so if you know what temperature your object is radiating at, then you just simply divide by that temperature in Kelvin, and you can get the lambda max from that. Okay. And that lambda that you get is going to be in micrometers. It's always funny to me, whenever I see formulas like this that have like a magic number. And so, like who in Mother Nature chose this number 2,898? So it's so random, but it's funny how nature just kind of works like that. Okay. Okay. And so we have this formula here. Okay. Right. And so we have this formula for the spectral emissive power, right? But you might be saying that we've already seen a formula for emissive power as well. Right? Okay. And so this is back when we first introduced radiation, right? And so what we said is that for a given object that's radiating heat, we can say the amount of power or the amount of heat flux that's coming off of it is equal to the following. And so we had epsilon sigma t to the 4th, right? Right. And if we assume for a second that epsilon is 1, right, because we have a black body, what we say is that E is equal to sigma t to the 4th. Okay. And so this is what we said is the emissive power for an object that's generating, that's radiating heat, okay? And so somehow, these two ideas have to be consistent with each other because we can't have two formulas for emissive power, right? This is no multiverse Spider-Man thing, right? There can only be one formula, right? And so there is a relationship in between these. And so let me go ahead and give that relationship, okay? And it has to do with the wavelength. Okay? Notice how in this formula, we don't have a wavelength at all. The only thing we have is temperature. And so the way that we obtain this is that we take our function of E lambda T, okay? Okay. And let me just to differentiate this, let me call this EB, okay? So black body emissive power. Okay? And so the way that we can set these equal to each other, okay, is that we have to eliminate the dependence on lambda, okay? And so we have to kind of get lambda out from the equation. Okay? And so one way that we can do that mathematically is we can just integrate, right? And so if we integrate, in this case, we're going to integrate over all wavelengths. Okay, so we're going to integrate from 0 to infinity, d lambda, right? That's going to equal to EB, right? And so if you take integral from 0 to infinity of 2 pi h c naught squared divided by lambda to the 5th exponential h c naught lambda kb minus 1 d lambda. Okay, this is equal to sigma t to the 4th. Okay. And so obviously, that's like we said before, this is not a function you want to take the derivative of. This is also not a function that you want to take the integral of too. I remember this very clearly when I first taught this, 3 years ago. I just kind of jokingly said that, by the way, this is a homework problem. You're gonna have to carry out this integral. I had literally someone say, "What the fuck?" out loud. And I said, "No, I'm kidding. I'm kidding. Even I don't want to do this." Okay, so of course I wouldn't make you guys do that as well, right? But that's kind of how we obtain this sigma constant here, right? And so this sigma constant, you can think of it as kind of the result of performing this integration. Okay. So that's kind of like that. Right? But what's interesting about this integral is that we're taking this integral across all possible wavelengths, right? And so that's why we're integrating between 0 and infinity. Sometimes we're not interested in all wavelengths, right? Sometimes we're just interested in just kind of a band of particular wavelengths, right? And so, for example, a lot of people are interested in how much heat is being emitted through a laser, right? So everyone's really interested in lasers. Lasers are really cool. And so if you know anything about lasers, lasers are kind of a concentrated beam of a very tight band of wavelengths, right? And so it's light. But it's only emitting between lambda 1 and lambda 2, where those are really close. Okay, and so a lot of times what you're interested in is not the entire spectrum here, but you want to find out what the power is just from a narrow band. Laser, yeah, literal lasers, yeah, the things that come out of Superman's eyes.
I think it's the lost powers.
Oh, it's been so long since I watched that. It's such a good movie. And so, we can modify the expression above by just integrating between, instead of 0 to infinity, between lambda 1 and lambda 2. Okay.
And so this right here is the banded formula for the banded emissive power. Okay. Where the band is defined as, what's between lambda 1 and lambda 2. Okay. And so again, we're actually not going to evaluate this integral, but people have tabulated it. Okay. Oh my God. Okay, and so you can find this table in the book, or you can just use what I have here in the lecture. And so that's going to be table 12.2 in the book. Okay. But using this table is a little bit strange. And so let me go ahead and cover how we can actually use this. Okay. And so if you look up that table in the book, it's going to look something like this. Okay. And so we're going to have two columns. The first column is going to be a product of lambda t. Okay. And the units for this are micrometers Kelvin. Okay. And the other column is going to be an F. And in parentheses is going to be F between 0 and lambda. Okay. And so it's going to look like this. And so I have no idea why that's happening. Okay. And so it's going to have 200, 400, 600. There's going to be increments of 200 basically. Okay. Okay. And on the right, you're going to have values here. So the first are going to be 0. This next one's going to be 0.00016. Next will be 0.0000, or excuse me, just 3 zeros. 32. Next is 0.002134. Then 0.007790. And then we'll do one more, 0.019718. Okay. Okay, and so we're going to use this table to perform the integral that we have above. Okay. And so the way that you use this is that, if you're integrating between lambda 1 and lambda 2, okay. And so those are your integration bounds, and so that's the band that you want to compute. Okay. What you're going to do is you're going to compute two quantities. And so you're going to compute lambda 1 times t. Okay? And so you're going to take your first wavelength and multiply it by the temperature. Okay? Then after you do that, you're going to look up the corresponding F value in the table. Okay? Okay? So let me call this F1. Okay? And so for lambda 1t, you're going to get a corresponding F. Okay? Then you're going to do the same thing with the other wavelength. Okay, so you're going to take lambda 2 times t, and this is going to give you another F2. Okay. Okay, and so once you have F1 and F2, then you can plug in, and so the E band is going to equal to sigma t to the 4th multiplied by F2 minus F1. All right, and so in other words, the way that we, the way that we compute this integral is that, for each wavelength, we multiply it by its temperature. We obtain an F value from the table. We do that for both. We take the difference between them, and then we multiply it by the black body emissive power, which is sigma t to the 4th. Okay. And so I have an example next that kind of shows you that process. Okay? And it mixes in a little bit of what we learned last time in terms of the hemisphere. Okay, so any questions on this before we do an example? Okay, all right. So let's see how this all plays out from through an example. Okay, and so let's consider the black body radiation from a surface that's 1500 Kelvin. Okay. And what we want to do is we want to compute the emissive power that's occurring through a cone. Okay. And so our cone looks like this. And so we have, so let me draw the surface first. Okay, so this surface right here. Okay. We're going to say this surface here is 1500 Kelvin. Okay. And what we're interested in is the amount of emissive power that's coming out, in this cone. Okay. So it's a cone that looks like this. Okay. If we do a vertical line, this angle right here is 60 degrees. Okay. And we want to do this in the following wavelength band. Okay. Okay. And so wavelength band is going to be 2 micrometers, which is less than or equal to lambda, which is less than or equal to 4 micrometers. Okay. And so our lambda 1 is going to be 2 micrometers, our lambda 2 is going to be 4 micrometers. Okay. All right, and so we're going to incorporate some concepts from the last lecture from last week together with this kind of table that we have here for the different wavelengths. Okay. Okay. Any questions on this? Okay. All right, so let's go ahead and start this problem. Okay. All right, and so the first thing we see here is that we're not computing emissive power for this entire dome. Okay. Okay. And that's significant because remember, we had this formula before where we said that emissive power is equal to pi times the intensity. Okay. But this pi right here, this pi was under the assumption that we were computing the radiation over an entire hemispherical dome. Okay. And so we can't assume that here. And so we're going to need to find out a different expression for pi, that only encompasses this cone right here. Okay. All right. And so the formula that we're going to use is going to use a formula for A. Okay. And so I call this area, but obviously it's not it doesn't really have units. And so we're going to assume this area here is of its hemisphere, but the radius is essentially 1. And so that's what you can kind of think of it. Okay. Right. And the way that we can compute it is we can take double integral of cosine theta, sine theta, d theta, d phi. Okay. Clean it up a little bit. this keep happening?
That only happened after spring break.
I know. My iPad is still on spring break. Okay, where theta here, remember, theta here is the azimuthal angle. Okay. And phi here is the polar angle. Okay. All right, and so the azimuthal angle is actually this one right here. Okay, so that's the angle that's with respect to the vertical axis. Okay. And the polar angle is the one that's occurring within the plane. Okay, and so this angle right here in the plane, this is theta. Okay. Okay, so let's set bounds on the integral here, that correspond to this cone. Okay, and so for this cone, it actually does make an entire circle in the polar direction. Okay, and so an entire circle in radians, that means that we go from 0 to 2 pi. And the azimuthal angle, this is where we vary, right? So normally for an entire hemisphere, we go from 0 to pi over 2, okay? Because that covers the entire upper half of here. Okay. But for this one, since we're just doing a cone, instead of 0 to pi over 2, we're going to do 0 to pi over 3. Okay. Okay. And so this pi over 3 right here, this corresponds to the cone. Okay. All right, and so we're faced with an integral here, but this is actually one that we can do, and so this is not one that we can pass. Okay. And so you might have seen this integral actually before. I'm sure this is a very classical integral that you might have covered in calculus or what. Okay. And so the classical way to solve for this is to use U-Substitution. Okay. And so we're going to set U as equal to one part of our integrand here. Okay. And so our U sub is going to be sine theta. Okay. And then we take the derivative of this, du, it's going to be cosine theta d theta. Okay. All right. And so this works out perfectly because not only do we have sine theta in our integrand, but we have cosine theta as well. Okay. And so what this allows us to do is it allows us to replace this entire integrand right here, which is u du. Okay. U-du. Okay, and integrating u is a lot easier, right? Because integral of u is just 1/2 u squared. Okay. All right, and so I'm not going to go through the entire mechanism of performing this integral. That's kind of more busy work at this point. But if you kind of work through that entire thing, with the u substitution, then what you get is a is equal to, instead of pi, what we have is 3/4 pi. Okay. So this is after integrating. Okay. And so what this means is that the emissive power here is going to be 3/4 pi times the intensity. Okay. Okay. And so let's take that information. And so what we say is that, let's go ahead and plug in for I now. Okay. And in fact, what we're going to plug in here is the banded expression for I. Okay. And so what we say is that E band is equal to 3/4 pi times integral from lambda 1 to lambda 2 of 2 hc naught squared divided by lambda to the 5th exponential hc naught divided by lambda kb t minus 1, okay, d lambda. Okay. Or remember lambda 1 is 2 micrometers, and lambda 2 is 4 micrometers. Okay. Okay, and so we're at the point now where we need to use the table to integrate, okay, because we can't perform this integral otherwise. Okay, and so let's go ahead and plug in our two values, right? And so remember what we have to do is we have to take lambda, we multiply by t. Okay. And so in this case, our T here is 1500 Kelvin. And so we take 2 micrometers times 1500 Kelvin, we end up with 3000 micrometer Kelvin. Okay. And so we look this up in the table, and what we get is F1 is equal to 0.273. Okay. And so I don't have that one listed on the table above, but it's in the one in the book. Okay. And then we'll get lambda 2t, right? And so once again, we'll plug in t is equal to 1500. As we take lambda 2t, that's going to give us 6000 micrometer Kelvin. Okay. And so this means F2 is going to be equal to 0.738. Okay. Right, and so if we take those results, then we can get E band. E band is equal to 3/4 pi times sigma t to the 4th times F2 minus F1. Okay. Right, and so we plug all that in, and we miraculously get a very nice number, because this is an example from the book. And so we get 10 to the 5th watts per meter square. Okay. And so that's the amount of heat flux, or of emissive power that's coming off of the surface. Okay. So it looks like a lot, right? So 10 to the 5th watts per meter square is nothing to sneeze at. Right? And so that's quite a lot of power. But remember, our temperature here is extremely high, and so we have 1500 Kelvin. Okay. And so to get that kind of temperature on Earth, would be very, very extreme. Okay, because that's about a little bit over a quarter of the power of a little bit over the quarter of the surface temperature of the sun. Okay, and we know how hot the sun is, and so it makes sense that something that's even a quarter of its power still produces a lot of heat. Okay, any questions on this example here? Okay, all right, so that's so all that is due to black body radiation. Okay, let's talk a bit about real surfaces now. Okay. And so remember, black bodies are an ideal case, right? And so there's kind of no such thing as a black body, right? Real surfaces have, they have emissivities and absorptivities that are less than 1. Okay? Okay. And we're going to focus mostly on the emissivity here. Okay. Right. All right. And so remember, we talked about emissivity last time, right? And so emissivity is some number between 0 and 1, right? And so the closer it is to 1, the better that surface is at radiating heat, the better it is at emitting energy. Okay. And so we can almost think of it as like a ratio. Okay? And so what we can say is that epsilon is equal to E actual, okay, where E actual is the actual amount of emissive power that's coming off, okay, divided by E black body. Okay. Right, so it's very similar. It's very similar to our definition for effectiveness of heat exchangers, right? And so our definition for effectiveness in heat exchanger was, in the denominator we have the theoretical maximum amount of heat that can get exchanged in a heat exchanger, right? And that's going to be underneath, how much actual heat that gets, that gets transferred, right? And so that's probably why they share the same symbols, just so that we can interpret it kind of the same way. Okay. But we just got done talking about the fact that emissive power, the capital E's, the emissive powers are going to change according to wavelength. Okay. Right. And so if the emissive power changes wavelength, that means the emissivity of a surface also changes with wavelength. Okay. Okay. And so we can actually plug in our formulas for, for E in this expression. Okay. So what we can say, another expression for epsilon here is that if we take the integral from 0 to infinity, of epsilon lambda times E black body d lambda. Okay. We divide this by integral from 0 to infinity of E black body d lambda. Okay. Right. And so depending on the types of waves that are coming off, or depending on lambda, you're going to have different emissivities as well. Okay. And so this is where things actually get really complicated with radiation and optics in general. Okay. Because any given object, let's say that we have this clicker right here, right? Okay. And so that clicker is going to give off different amounts of radiation in different wavelength bands, okay? Because its emissivity is different, right? That's part of the reason why when we look at this clicker, first of all, it has different colors, right? I mean, it's mostly black, but it has a little bit of white and red, right? But the surface also looks a little bit different as well, right? So we have shiny parts, we have rough parts, right? Right. And part of that is due to the fact that, for the different parts, the different materials on this clicker, it's going to be radiating heat or radiating light, more effectively in different wavelength bands. Right? And so if you ever, I've never done this, but, I've had friends that have done this. And so, if you ever take an advanced class on like optics or electromagnetic waves, it gets very hairy very, very quickly. And so, I remember when I was a student, it really turned me off. And honestly, it still turns me off now. It's lambda, so d lambda. So both integrals are with respect to lambda. Because what can also happen is that not only do these things vary in terms of lambda, in terms of wavelength, but they can also vary in direction as well. So that's when things get really, really messy. And so, optics is really crazy. Okay, but we can do like a very simple example here to kind of show you, illustrate what's going on. And so let's say that we have a diffuse surface that's 1600 Kelvin. Okay. And so all diffuse basically means is that it's emissivity and absorptivity are the same. Okay. But we'll go over that more and over the next couple of weeks. Okay. Okay. And so what we say is that it has the following spectral emissivity. Okay. Right. So remember the key word there is spectral. And so spectral, all that means is that it varies according to wavelength. Okay. Right. So we have two bands here. So we have, it looks like this. Okay. This right here is 2 micrometers. This right here is 5 micrometers. Okay. And so this emissivity here is 0.4. And this one up here is going to be 0.8. Okay. And so our emissivity here is going to vary between 0.4 and 0.8, depending on the wavelength of the wave. Okay. Okay. And so based on this graph, we can find a couple of things. And so we can find and so first of all, we can find the total emissivity. And so that's going to give us an overall epsilon. Okay. And 2, we can also compute the total emissive power. Okay. Okay. And so that's going to be E. Okay. Right. And so we're no longer working with black body radiation here. So, this radiation is going to have some epsilon. Okay. Okay, so let's go ahead and use the formula that we have up here. Okay. And so what we can say is that the total emissivity epsilon is equal to integral from 0 to infinity of epsilon lambda EBB. Okay, BB stands for black body. Okay. D lambda divided by integral from 0 to infinity EB B D lambda. Okay. And so in the numerator here, I'm going to go ahead and plug in our bands. Okay. And keeping in mind what the value of epsilon lambda is, right? And so our first band is going to be between 0 and 2. And so in the numerator here, we're going to have integral from 0 to 2. Okay. And the value for epsilon lambda here is just a constant. It's equal to 0.4. Okay. Okay. And so that's the first band. Okay. So the denominator we keep the same, because remember the denominator we assume that to be kind of the maximum amount of radiation. So that's the total black body radiation. And so that's why in the denominator we keep the integral from 0 to infinity. Okay. And so that's our first band. Our other band here goes between 2 and 5, right? And so we're going to take integral between 2 and 5. Okay. The value of epsilon lambda there is 0.8. Okay, so we're going to multiply 0.8 out in front. Okay. And we just fill in the rest of the expression from there. Okay. All right, and so we're faced with these integrals there, and so I'm not going to plug in the entire expression for the integrals, but because we're integrating the spectral emissive power, we can use the same tables to perform these integrals. Okay. One other thing that we can plug in that's going to simplify our work a bit Because we can plug in for these denominators, right? Okay. Because we know that, if we integrate over all wavelengths, then the black body emissive power is just going to be sigma Ts to the fourth. Okay. Right. So that was the integral that we discussed earlier that I kind of joked was a homework problem. So, when we integrate from 0 to infinity, all that gives us is just sigma Ts to the fourth. Okay, all right, so let's go ahead and perform these integrals. Okay. All right, question. So can we not just find the area under the curve by using the graph for the numerators? So there's a couple of things. And so, what we have here is just how the emissivity kind of varies with wavelength, but then you have to also combine it together with the black body emissive power as well, because that also gives you that also contributes to how the emissivity is kind of in total. Yeah, I know what you mean. And so it's tempting to just kind of look at this area right here, but it's also kind of modulated by the fact that we also have the black body radiation there, or the not black body, the spectral emissive power there as well. Okay. And so let's go ahead and compute our lambda t's here. And so we have lambda 1 t, okay, or lambda 1 here is 2 micrometers. Okay. Okay, so lambda 1 t here is 3200. Okay. Lambda 2t, or lambda 2 here is 5 micrometers. Okay. We plug in for that, you get 8,000. Okay. And both of these are micrometer Kelvin, micrometer Kelvin. Okay. And so let's go ahead and look these values up in the table. And so for F1, corresponding to 3200, we get 0.318, excuse me. And for F2, we get 0.856. Okay. All right. And so let's go ahead and plug these in. And so we have, first we have integral from 0 to 2 of EBB d lambda. Okay. And so this is going to be equal to sigma t to the fourth times F1 minus 0, okay? Because the lower bound here is 0. Okay. And then our second integral there is going to be sigma t to the fourth F2 minus F1, because it's a banded integral between 2 and 5. Okay. And so if we plug all this in, then we get epsilon is equal to 0.4 times F1 sigma t to the fourth divided by sigma t to the fourth plus 0.8 times sigma t to the fourth times F2 minus F1, all divided by sigma t to the fourth. Okay. And so all the sigma t to the fourths are going to cancel out. Okay. And so all we're left with is just those expressions there, which you can easily plug into a calculator. Okay. And what we get from all of that is 0.558. Okay. And so that's the total emissivity of this surface, okay? Kind of accounting for all the wavelengths. Okay. Okay. All right. Any questions on how we did this? How we got this result here? Okay. Okay, and so now let's do the second part of the problem. And so the second part of the problem is to find the total emissive power. Okay. Okay. So the good thing is that, we've already taken care of the band, right? And so the fact that, we're basically banded here between 0 and 5 micrometers, okay? And so we've already taken care of that in our epsilon, okay? Okay. And so instead of performing the integration all over again, what we can say is the total emissive power is equal to epsilon, the one that we just computed, times sigma times t to the 4th. Okay. Where this epsilon here is 0.558, right? And so we go ahead and plug in all the values for this, and what we get is 207 kilowatts per meter square. Okay. Right. And so kind of the benefit of kind of doing those integrals ahead of time by accounting for that band, then all of our other calculations are going to be a lot simpler. Okay. And this is actually going to be really useful because, I think so starting next week, we'll start talking about radiation exchange. And so, the radiation exchange between separate surfaces. And we're going to be using we're going to be using epsilon values there. But our assumption is going to be that those epsilons have already taken the different wavelength bands into account. Okay. And so this is kind of a nice, convenient way to kind of, package kind of a lot of what we just learned into kind of just a single variable. Okay. And so for a lot of what we're going to do from now on, we're going to assume that epsilon kind of takes those wavelengths into account already. Okay. And so we have about, 7 minutes left. And so I want to talk a little bit about irradiation, just because we've been talking about emission this whole time. Okay. And so we've kind of just been talking about just one side of the radiation story, right? And so, we've known up to this point that, radiation is emitted from all objects, right? But radiation can also be accepted by objects as well, because that radiation has to go somewhere, right? And so it has to hit onto an object. And so remember, whenever we talk about radiation hitting an object, we call that irradiation. And irradiation is a little bit more complex because, it can do several different things. Okay. And so first thing it can do is that it can absorb, okay? Right, and so absorption is kind of the, kind of the heat transfer, thing that we're most concerned about, right? And so because when radiation hits an object and it's absorbed, that means that the thermal energy of that object is going to grow, okay? And so that's heat transfer. And so we focus mostly on emission and absorption because, this is a heat transfer class. It's not an optics class. But I do want to make you aware that radiation can do other stuff as well. Okay. And so number two is that the radiation can just simply reflect, right? So it can just simply bounce off and come back. Okay. And so a lot of your reflective surfaces will do this. Right? And the third thing you can do is transmit. And so that's radiation that just passes right through an object. Okay? And so it doesn't get absorbed, it doesn't reflect, it just passes right through. Okay? And so any kind of your transparent objects will have this as well. Okay. Okay. And so, we're not going to spend much time talking about it, but basically the upshot is that, the way that we can quantify these things is exactly the same way that we quantified emission above. Okay? And so what we say is that these different properties also depend on the wavelength of the radiation that's hitting it. Okay? Okay. So very much in the same way like the previous example. Okay? And just like the previous example, we can actually use the same integral formula to quantify these. And so I'm not going to write it down for all of them just because it would take too long, but I'll show you an example with the absorptivity. Okay. So remember this alpha here corresponds to absorptivity. Okay. And so we define it as the ratio. And so we take the G. So G is the symbol that we use for, for irradiation. And so the amount of radiation that gets absorbed, okay, divided by G total being the total amount of radiation that hits a surface. Okay? This is equal to integral from 0 to infinity, alpha lambda, EBB d lambda, divided by integral from 0 to infinity, EBB d lambda. Okay. So basically exactly as what we had above for emissivity, but we're doing things in terms of absorptivity instead. Okay. All right. And so, we can use a lot of terms to describe these quantities, based on their optical quantities. Okay. And so, if a word that we've used a lot, or we use typically in normal conversations is opaque, right? And so if an object is opaque, that means that we can't see through it, right? And so it's kind of a solid object. It's like the wall over there, right? We can't see through the wall. And so if an object is opaque, that means its transmittance is 0, right? And so that wall doesn't transmit any light waves through that wall, right? So that's why we can't see through it. On the other hand, if an object is transparent and we can see right through it, then we say the transmittance is 100%. It's 1.0. Okay. And anything between is translucent. Okay. And we also know reflective surfaces like mirrors. We say that those have a reflection coefficient of 1. Okay. And so, a lot of this terminology that just from kind of general optics and general conversation, they apply to heat transfer as well. Okay. All right. So a bit of trivia as we ended the lecture today. So are there any final questions on this before we wrap it up for the week? Okay, all right, so that's all I had planned for today. And so next week when we pick it up again, we'll start talking about radiation exchange. Okay, and so that's basically the exchange of heat, between surfaces via radiation. Okay. Oh, questions? How did I get 207? So I got 207 by plugging in 0.557 or 558, excuse me, for epsilon. Sigma here, I plugged in Boltzmann's constant. I forgot it already. So Boltzmann's constant is 5.67 times 10 to the minus 8. And the temperature for this one was 1600. And so I take 1600 Kelvin to the raised to the 4th power. Yeah. Okay. All right, so thank you guys for coming today. I apologize for, kind of the mix up. I wasn't sure when the plumber was gonna come, but, I did make it to campus today. And so hope you guys have a good weekend. I'll have your midterms back to you by Monday, and I'll see you guys then. Thanks. Have a good weekend, everybody. Hey, how's it going? What? What? I wasn't sure if the plumber was gonna come or not.
I have a question.
Yeah.
When did we define emissive power and intensity to be pi?
Yeah. So the pi actually comes from the fact that, if you remember from last week, let me see. When we were talking about radiation, we were talking about the fact that it kind of extends out equally in all directions.
Right.
And so we had this idea of like a dome, like an hemisphere. And so everything on this dome is equidistant to that. And so what we can say is that, if you can take the surface area of a dome, and so that's going to be half of a sphere.
Yeah.
So that's 4 pi r squared. Right? And so what we say is that, this is kind of a normalized area for this half. And so so that's we just say it's pi. Yeah. Yeah. So that's why in that example, we, instead of pi, we did 3/4 pi because it was only a cone instead of a dome.
Got it. Okay.
Yeah.
Thank you.
Yep. Mhm.